So now we're in module number 2, lesson number 4, and our journey in discussing Eigrp and all the different aspects of Eigrp. We pretty much covered just about everything that there is related to the concept of. Oops. We've discussed everything there is kind of related to the concept of the theory of Eigrp and all the different components that are covered within Eigrp from a theoretical standpoint. So now we're just going to wrap up the module by simply talking about how do we do this and how do we implement Eigrp for Ipv6. And then finally we'll wrap up the module by talking about named configuration and how we're going to kind of consolidate the configuration of Eigrp by using a more modern approach to configuring Eigrp. So let's start by getting into lesson number 4, configuring Eigrp for Ipv6. Eigrp was actually designed originally as a protocol, a routing protocol that would integrate easily with IPv4 and IPX. IPX, if you guys recall, another network layer protocol that allowed us to communicate over the network layer for Novell. But obviously it's been deprecated. We don't really see that protocol too much these days. But because the Eigrp was designed to be useful for multiple network layer protocols, adapting it to work with IPv6 was relatively simple. And you're going to see that essentially just about everything that we did over the past day, essentially, with all the other Eigrp stuff, really kind of transports or easily carries over to what we're going to be talking about today or this morning. The only exception to that is when we take a look at the authentication piece within Eigrp, because IPv6 has IPsec built into it. It has the IPsec protocol suite or framework, if you will, built into it. And the authentication piece is significantly different in that case when you decide to implement authentication for IPv6 versus authentication for Eigrp for IPv4. And we will get to that. We're going to talk about how authentication works in these protocols in module number 7. All right, so let's talk about the differences and the similarities between Eigrp for IPv4 and IPv6. We'll take a very quick look at, through a discovery, basic Eigrp for IPv6 settings. We'll take a look at how we set up summarization, and then we'll also take a look at how we verify Eigrp operations for IPv6. All very simple concepts, and then I'll probably dive a little bit deeper into these concepts by also taking a look at some of the other configurations and some of the other options that we looked at in IPv4 as well. All right, so that's what we're looking to cover in this particular lesson. Let's start by taking a look at kind of a side-by-side comparison, Eigrp for IPv4 versus Eigrp for IPv6. Link local addresses, those FE80 addresses that we talked about when we were talking about just in general IPv6 addressing, that doesn't exist in IPv4. However, it does exist in IPv6, and that's actually how our neighbor adjacencies are formed in Eigrp for IPv6 utilizing those link local addresses. Remember, we talked about the concept that these link local addresses just play a really significant role in how we manage relationships, how we manage the routing table, how databases are managed, and so on. And we're going to see that in this discovery here. Automatic network summarization, not something that we typically would want to run anyway, is only available in IPv4 because IPv4, if you recall, had the concept of classful versus classless, whereas IPv6 has never been defined as a classful routing protocol or a classful addressing scheme in any sense. IPv6 has always been classless, so we never had the idea of major classful boundaries in IPv6. As far as the layer 3 protocol that's used for transporting our Eigrp messages, obviously we're talking about IPv4 versus IPv6. The authentication piece, as I was just mentioning, Within IPv4, we have EIGRP specific configurations, typically using MD5 hashing and challenge-based authentication. Whereas in IPv6, we simply use the authentication header and encapsulated security payload features, essentially AH and ESP are IPsec, that's natively built into the IPv6 protocol. All right. In fact, OSPF does the same thing. OSPF has OSPF-specific authentication methods for IPv4, but it also makes use of the IPsec framework that's built into IPv6 for any kind of IPv6-based authentication. The multicast address, 224.0.0.10, or FF02:A. We had talked about that previously. We also talked about the fact that EIGRP is encapsulated directly in inside of IP. There is no transport layer function, so it's protocol number 88 in both cases. As far as the metric goes, as far as all of the other concepts that we talked about, feasible distance, feasible successor, the feasibility condition, the idea of variance to do unequal cost load balancing, maximum paths, all of those concepts are identical in both EIGRP for IPv4 and IPv6. So that's the nice thing about this process, is that you don't have to relearn everything all over again because we're moving over to IPv6. Essentially, all of the theoretical concepts are identical, and we're going to discover that as part of this process. So let's get into discovery number 7. I've already got discovery number 7 loaded, where we're going to go ahead and just simply configure EIGRP for IPv6. It's only a single discovery, so we're going to take a look at a lot of the concepts that we covered throughout the last few modules in IPv4. We're going to look at them in one concise format here under the IPv6 EIGRP discovery section. So we've got 3 routers, HQ with 2 WAN connections. 2001 DB80 is our /48 prefix for our entire enterprise. And then we have various subnets. This is subnet 100. This is subnet 200. This is subnet 16 back here. And then we have subnet 0, 1, 2, and 3. So we're going to enable EIGRP for IPv6 on BR2. We're going to verify the operation of EIGRP for IPv6 on our HQ router and our BR1 router. And then we're also going to configure summarization. And I will try to demonstrate a couple of other concepts as well as part of the process when we go through the final wrap-up, if you will, for this particular section. There's a few things missing in this chapter. I just want to demonstrate those concepts just to make sure you guys are aware that those similar concepts exist, but there are some slight differences in how those things are configured. So we'll take a look at variance. Even though we don't really have redundant paths here, we don't have the ability to do unequal cost or even equal cost load balancing in this particular case. I still want to show you guys the syntax and just demonstrate the fact that the syntax is very similar. All right, so let's start the exercise by implementing IPv6 for EIGRP on BR2. The first thing that we're going to have to do, of course, is enable IPv6 routing on that particular router. So let's start by taking a look at the router configuration on BR2. And just like we had a concept of, show IP protocols and show IP interface brief and whatnot, we have similar commands in IPv6. In fact, in a lot of cases, if you simply replace the IP with IPv6, you can get a lot of the same outputs. For example, show IPv6 interface brief instead of show IP interface brief. And we can see the interfaces that are configured on our device. We got our loopback here. We've got our Ethernet interface, Ethernet 1.0. I could do a show IPv6 protocols as opposed to show IP protocols. So I can see that IPv6 routing is actually already enabled. If I do a show run include IPv6. I'll probably see that the IPv6 information is applied, but you can notice here that I do not see IPv6 unicast routing. So if I were to try and enable IPv6 for EIGRP right now, it would give me an error, and so that's somewhat unique in this particular case, right? Because traditionally, if I wanted to put IP addresses on a router interface, I would have had to go in and actually do IP routing before I could even do that. In IPv6, you can actually assign IPv6 addresses to interfaces without having that router act as a router. For example, let me show you real quick. Let's do which interface are we talking about here? Ethernet 1.0. So let me do a show IPv6 interface Ethernet 1.0. And what we can see here is that this interface does have IPv6 enabled. It's got a global unicast address. It's got a link local address. But notice that it's not participating in the FF02:2 multicast group. It's only participating in the FF02:1 multicast group, which, by the way, is the all hosts multicast group. If I come in here and I do IPv6 unicast routing, and now I go back and check that same interface, you'll notice that now it is participating in the all routers multicast group. So previous to entering that command, IPv6 unicast routing, the router was simply acting as an IPv6 host as opposed to a IPv6 router. So that's a little bit unique from what we see with IPv4. But we don't usually have to deal with the IPv4 piece because IPv4 routing is almost always enabled on the routers by default. All right, that's essentially just something that just exists by default. We don't really have to worry about it. I mean, you could go into a router and you could actually technically come in and say, okay, I don't want to do IPv4 routing on this router, so I'm going to do a no IP routing, right? And that will turn off the IPv4 protocol stack, but we can still see that we're running the IPv6 protocol stack. So IP routing is basically a command on routers that's just enabled by default, but not the IPv6 unicast routing command. So we need to make sure that we implement that. The next step as part of this process in implementing IPv6 for EIGRP is to go ahead and enable the IPv6 EIGRP process. Let me do one more show IPv6 protocols, and you can see that really hasn't changed much. We still have connected and we still have ND. ND stands for neighbor discovery. Incidentally, that is the process in IPv6 that replaced the ARP process in IPv4. In IPv4, we had the address resolution address resolution protocol, which allowed us to discover MAC addresses when we didn't know them based on an IP address that we knew. If I do a show ARP, obviously in this particular case, we're not going to see anything because we're not running IPv4 in this particular exercise. But there is no show, quote unquote, show ARP command for IPv6. Instead, it's show IPv6 neighbors. All right, and we can see that we already have a neighbor. This is the MAC address of the neighbor. This is the link local address of the neighbor. So again, another difference between v4 and v6 is that in this particular case, we are mapping link local addresses to MAC addresses, not global unicast addresses to MAC addresses. So again, just another example of where that link local address plays such a significant role in the overall communication process. So it's really important that you understand the impact of link local. You understand potentially how to even manipulate link local addresses, because this is a much easier link local address to see than the traditional EUI64 address that we talked about previously. All right, so let's go ahead and get EIGRP for IPv6 enabled on this router. We're going to do that by typing IPv6 router EIGRP, and then we're going to choose an autonomous system number. just like IPv4, it's technically a 32-bit field within the EIGRP packet header, but the ASN is based actually on a 16-bit number. So it goes from 1 to 65,535. ASN 0 is not usable, obviously, in this case. So we're going to go ahead and apply ASN 100. You will notice that automatically we do not form an adjacency. And I mention that only because of how EIGRP is configured for IPv6 versus IPv4. We saw this in the RIP next generation configuration that we did previously, actually on the first day, right? Which was enabling the global routing process, but then going into each interface and applying that routing process to an interface. In other words, we don't use network statements. The same applies here. In this particular case, we're not going to use network statements to establish a routing process. We're going to actually enable the routing process directly on the interface itself. We'll see a similar thing when we get into OSPF for v3, OSPF for IPv6 as well. However, if I do a show IPv6 protocols now, you will see IPv6 protocols. You will see that we are actually running EIGRP 100. But there's something missing here, all right? And that's this right here. No usable router ID found. If you guys recall, we discussed the process of router ID selection in IPv4. It could be manually configured, or it would pick the highest IP address on an active loopback interface, or it would pick the highest IP address on a physical interface. All of those are great things, except for the router ID has to be written in a dotted decimal format. Well, we don't have any dotted decimal addresses on this router. We're not running dual stack. We're running v4 and v6 at the same time. So in order for us to be able to establish this process, in order for us to be able to establish the router ID, in the case of a router that you're only running v6 on, you have to manually configure the router ID. Because even in EIGRP for IPv6, that router ID is written in a dotted decimal format. Again, it doesn't have to be an IP address. It just has to be a 32-bit address that's usable in a dotted decimal format. We're going to go ahead and use an address like we would traditionally, but again, it could be 0.0.0.1 or 2.2.2.2 or whatever you want it to be. You know, just has to be unique within the entire domain. All right, now if I do my show IPv6 protocols, we can see that the router ID has been established as 192.168.2.1. All right, something that you definitely have to be aware of, especially when you start to get into configuring OSPF, particularly OSPF for IPv6, because the router ID in OSPF plays such a significant role in the overall process. All right. However, we can still see that we don't actually have EIGRP running on any of our interfaces. We see that the protocol has been enabled. We can see that the K values are what we expect to see. K1, K3 is 1, K2, K4, and K5 are 0. Metric calculations are exactly the same, bandwidth and delay, where bandwidth is 10 to the power of 7 divided by the worst bandwidth along the path in kilobits per second times 256, and the delay is the sum of the delays in tens of microseconds, or in microseconds divided by 10 times 256. So it's the same calculation. We can also see that the administrative distance for IPv6 is the same. Internal is 90, external is 170. This is a slightly different output, right? In IPv4, by default, the maximum number of paths that we would load balance over was equal to 4, but in the case of IPv6, it's 16 by default. In IPv4, it could go anywhere from 4 to 16, in IPv6, it starts at 16 and it can go all the way up to, I believe it's 64. Let's see, maximum paths, in this case, 32. All right, so it's probably OS specific, but in this particular case, we have up to 32 possible paths that we could load balance across. As far as everything else goes, though, the variance to default variance is 1, and maximum hop count is still 100 because that's simply a limitation of the protocol itself, whether it's v4 or v6. So that's a great thing, you know. We don't have to relearn everything as we move over to IPv6 with these particular protocols. They operate essentially the same way. So let's do a quick show IPv6 route pipe with include for my connected routes. So these are my connected interfaces. 2001 DB80:16:/64 and the 200 subnet. Let's do a quick show IPv6 interface brief. So that's going to be my Ethernet 00, or excuse me, Ethernet 10 interface and my loopback 0 interface. So we're going to go ahead now and enable the EIGRP routing process on those interfaces. We do not use the network statements anymore. We simply go into the interface that I want to enable the protocol on, and I execute a command to enable the protocol on that particular interface. So interface loopback 0, IPv6 EIGRP 100, interface Ethernet 10, IPv6 EIGRP 100. All right, that's it. We've enabled EIGRP. We see that we get an adjacency formed, and that makes our life maybe a little bit simpler. Although some would argue that it actually makes it more complicated, because rather than having kind of a generic network statement that includes a whole bunch of interfaces, I actually have to physically touch every interface and configure EIGRP on each of the interfaces. Now if I do a show IPv6 protocols, I can see that do show IPv6 protocols. I can see that we've now enabled EIGRP on our loopback interface and our Ethernet interface. You know, all of the commands that we were used to using with IPv4 translate over to IPv6. For example, to show IPv6 EIGRP neighbor. All right, exact same format. We've got our host index column, we've got our address column, we've got our interface column, our hold time. Even the hold time values are the same. In the case of Ethernet, that's 5 and 15. Right, 5-second hello timer and a 15-second dead timer. We've got our uptime, smooth round trip time, retransmission timeout. All of these values are exactly the same as they were in IPv4. The only exception is that the neighbor adjacency is being formed with a link local address as opposed to like a global unicast address. I can add the detail option if I want, and I can see, you know, the number of prefixes that I'm receiving from a particular neighbor. If I wanted to do a show IPv6 EIGRP interface, I could do that as well. And again, I'll see which interfaces are running EIGRP, how many peers they exist, and so on. So again, all of the other commands that we've seen throughout this whole process still exist, and they're implemented exactly the same way in IPv6. How about the topology table? Let's take a look at that. We've kind of progressing through our data structures here, right? We take a look at our neighbor table, make sure we have our neighbors. Topology table is everything that we're learning. So if I do a show IPv6 EIGRP topology, I can see my topology database. And it's actually formatted exactly the same way. The only exception is, instead of v4 prefixes, we're seeing our v6 prefixes, and instead of a v4 IPv4 next hop address, we've got a link local IPv6 next hop address. But as far as what's in the brackets, this is the feasible distance of that particular route. This is the reported distance or advertised distance of that route. We have our successors. We would have our feasible successors if they were listed. We would also have the all-links option as well. Remember, the all-links option would show us paths that did not qualify as a successor or feasible successor. So, you know, there's really no reason to be kind of nervous or you know, have trepidation about configuring IPv6 for these protocols, because you don't have to relearn everything based on your understanding of how the IPv4 version worked and the hours and hours that we did talk about that, right? Let's take a look at the routing table in BR2. Do show, let's get out of config mode here. All right, show IPv6 route, Eigrp. And the routing table looks very much the same. The format is slightly different, but we still have all the same elements, right? We have the code that indicates how the route was learned. And by the way, we would still see D or DEX. We have the destination prefix. We have the administrative distance, the metric, the next hop, and the exit interface. So the only thing that's really missing from this that we saw on IPv4 was the age of the route, right? That's one piece that's kind of missing here. All right. We can do all kinds of things like ping as well. Incidentally, for you guys that are looking to take your T-shoot test, if you haven't already taken it, that's the third part of this three-part series to get your CCNP. There will be at least 3, possibly 4, but at least 3 IPv6 tickets on the troubleshooting test. Make sure that you pay attention to the vocabulary in the ticket itself, because you're going to start to get into the habit of going through the process of doing your v4 troubleshooting, and you're going to open up a v6 ticket and automatically assume that it's a v4 ticket, and all of your v4 troubleshooting steps are going to work, and you're going to be like, wait a minute, there's nothing wrong with this topology. It's all working, except for it's an IPv6 ticket. So you need to make sure you use all your IPv6 commands, not IPv4 commands. I've seen it happen a few times where students get into that test and they're just knee-deep in doing IPv4 troubleshooting, and then they all of a sudden realize, oh wait, this is an IPv6 ticket, so troubleshooting IPv4 is totally useless. All right. So we can do a ping. Let's go ahead and ping one of the addresses on our HQ router, 2001 DB8, not case sensitive, by the way, 1:1, and we do have to specify a source when we're doing a ping. Well, actually, in this particular case, because we're pinging a global unicast address, we technically don't need to specify a source. But if I want to check actual routing, I could specify a source of a different interface. In this case, I'm just going to specify a source of my loopback 0. So that tells me that I can route from LAN to LAN, essentially, because our loopback interfaces are simulating a LAN connection. All right. So we've got reachability, and again, we can ping ping link local addresses as well. We don't necessarily have to ping global unicast addresses. Link local addresses are only reachable within the local broadcast domain. So we can't ping link local addresses that exist on other devices, but are beyond the next router, but we can certainly ping all the link local addresses that are common to our broadcast domain and our subnet. All right. So let's take a look at how we can configure summaries in Eigrp for IPv6 as well. There's the command that we use to set our router ID, 192.168.2.1 in this case. These are the commands that allowed us to enable Eigrp directly on the interfaces. And then finally, neighbors, how to verify our neighbors, topology table, feasible distance, successor, all those concepts remain the same. And this is our routing table. All right. But now we want to go ahead and configure some summaries. And how do we do that in IPv6? Well, guess what? It's exactly the same as it would be in IPv4. All right, let me demonstrate. right? I think I kind of already did this demonstration in one of my previous exercises, but we'll go ahead and do it again. Let me get rid of that dialog box there. All right. Let's go ahead and just take a look at an example again. They do have one in the book here, but I kind of want to demonstrate this concept again. But let's say I wanted to summarize double colon, let's do A double colon / 64 and and B and C and E. All right. So I want to summarize these 4 networks into a single summary. Obviously, our goal here is to be able to identify what are the common bits versus the uncommon bits. And I think everybody would agree that 2001, DEAD, BEEF are definitely common between all of these networks. All right. So alpha in this particular case would be 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. That would be A. Remember, leading zeros in an IPv6 address do not have to be written in each hextet. So technically, this is 000A, but we don't have to write the leading zeros. It's just kind of inferred. That's part of the shorthand notation for IPv6. So it's not just 4 bits here. It's still 16 bits because it's a hextet. We just didn't write them down. So let's do Bravo. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. And Bravo would be this value. And Charlie, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, which would be this value, 12. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. And then finally 1, 1, 1, 0 for echo. All right. So if you look at the bit pattern here, it's actually quite obvious that these bits to the left are the common bits. And the bits to the right are the uncommon bits. So those would have to end up being removed from my summary because they don't match. So our summary address would be the value, our starting address, excuse me, would be the value of this address here, which in this case would be :8, right? Because this is my 8 placeholder, 1, 2, 4, 8. That's my powers of 2 to the power of 3. It gets me 8. And then I simply count the number of bits. So I know that the entire first 4 hextets is 64 bits, so I just subtract the 3 here, which gets me down to 64, 63, 62, 61, and that becomes my summary for those networks. It's going to include network 0, it's going to include network 1, network 2, network 3, excuse me, my mistake. It's going to include network 8 plus these 3 bits, right? So it's going to include network 8, network 9, network 10, network 11, network 12, network 13, network 14, and finally network 15. So essentially 1000 through 1111. All right. So the point here, obviously, is that it's done the same way as it is in IPv4. We're simply just comparing the common bits between all of the addresses that we're trying to summarize. And then finally, we're just simply calculating that the mask based on those number of bits. Make sense? All right. And they show you the same example here in the book. In this case, 2001 DB8. And then they're expanding. They're kind of mixing and matching here. The first 3 hextets are written in hexadecimal format, and then the last hextet is written in its binary format. So that's why you see so many digits in that last hextet. But they're doing that because they're trying to compare the bit patterns between each of those addresses. And that becomes my summary route, right? 62 common bits between each of those networks. the value of the bits in bold becomes my summary address, and then we just simply count the number of common bits, and that becomes my summary mask. All right. Now the question is, how do I configure that so that we can summarize? If you go back to our topology here, our goal here is to summarize these 4 networks on BR1 out to the rest of the network. All right. Well, that means that I need to create a summary. And in EIGRP, we assign summary addresses, or the summary address command, to a physical interface. Specifically, the interface that I want the summary to be generated on and sent into the rest of the network. So we're going to create this summary on Ethernet 1.0 on BR1. So let's go into BR1. We'll just do a quick verification. Show Ipv6 Eigrp neighbor. And we have our neighbor relationship. So I know that we're running Eigrp. We've established an adjacency. Show Ipv6 interface brief. And I can actually do a pipe include 2001, and I can see the different addresses that are included in my router here. 0:1:1, 0:2, 1, and 0:3, 1. It looks like we're missing, no, it's right here. So actually this is our 0, 0. The reason it looks different is because we're representing the largest consecutive blocks of zeros with simply a double colon. So we have 4 networks that we want to summarize, 0, 1, 2, and 3. We're going to do that on interface Ethernet 1.0. If you recall, we use the IP summary address command, Eigrp 100, and we put in the summary for Eigrp for Ipv4. Well, guess what? Just simply replace Ipv6, and we're going to use the same syntax. The only difference is that when we specify our summary, in this case, db8:/62, we are specifying obviously a v6 prefix instead of a v4 prefix. I mean, technically it is db8:0:/62, but we don't need to write out those zeros because they're inferred by putting in the double colon. All right, so that becomes, oops, I forgot my autonomous system number. That becomes our summary address for that particular route. All right, just like we saw on IPv4, if I do a show IPv6 route, you will see a null 0 route being created because we have that summary. Let's see, it's probably up here at the top. Where's my null 0? Loop back, loop back, loop back. There it is, just as I suspected at the top. We can also see it has a local administrative distance of 5, which we know that's what summary routes in a local router are represented as. So we still have our null 0 route for loop avoidance. And then if I go to my HQ router, I'm going to see that route specifically, show IPv6 route Eigrp. And we see that summary route right here coming in with an administrative distance of 90. The next hop is FE80:100:2. And yeah, we're good to go. All right. Same concepts, just slightly different syntax. I keep saying the same thing over and over again, but it's just really an important point. It just means that the idea of configuring Eigrp for IPv6 or OSPF for IPv6 or any of these other protocols for IPv6 isn't that difficult to do. All right. We've already done several of the different verification options. Let's just go ahead and get through some of these slides here. So there's the summary that we just created on Ethernet 0.0 in their case on BR1. There's the route that we see on BR2, so we didn't actually check that, but the route is definitely propagating over to HQ, and conversely, it's going to propagate over to BR2. All right. As far as verification goes, show IPv6 protocols. We can see all the things that I've already pointed out. One of the things I wanted to mention too was this concept of like passive interface and metric weights and variance and all this. All of these things are available to us, right? If I go into my IPv6 router EIGRP 100, I can see that I have all of the options like maximum PAS, passive interface, variance, as well as some other things that we haven't talked about yet. But all of the standard features, like if I wanted to set a variance, it still goes from 1 to 128 in this particular case. If I want to make an interface passive, I can choose the interface just like I would in IPv4. So again, a lot of the same concepts that existed in IPv4 exist in IPv6 as well. Metric calculations are exactly the same. We do a show interface, Ethernet 1.0 as an example to get our bandwidth and our delay, and those numbers go into calculating the metric for that particular interface. I still go into the interface to set the bandwidth if I want to set the bandwidth in kilobits per second, or if I want to set the delay in tens of microseconds, because those commands are not specific to EIGRP. It's just a way of manipulating EIGRP into doing whatever we want it to do. Okay? So before we wrap up this lesson, any other questions about EIGRP for IPv6? Outside of course, authentication, which we'll see a little bit later on. All right. So that actually concludes that lesson. What we're going to talk about next, actually I'm going to have you guys do a challenge lab, and then what we're going to talk about next, which is our last discussion, is what we call a kind of a modern approach to configuring EIGRP, which is named EIGRP configuration. So we'll see you guys in the next lesson.